Hi everyone, I am Mohammed Sheraz Anjum and I am presenting this research on behalf of myself and my co-author Conor. The title of our research is Seeding Grammars in Grammatical Evolution to Improve Search-Based Software Testing. To the best of our knowledge, we are the first to propose seeding in a grammatical evolution-based system. Our seeding strategy is different from conventional strategy as we are not actually injecting the knowledge in the initial population. Rather than that, we are actually injecting the knowledge in the grammar itself, which have its own benefits that we would discuss through my presentation. And for now, we are using this seeding strategy in search-based software testing, but we believe that there's a huge potential to use this strategy in any GE-based system, particularly the ones which have constants or other low-level structures involved. So in software testing, branch testing or branch coverage testing is a very commonly adopted testing criteria. So what it requires that all the true and false outcomes of all the branching conditions must be taken at least once. So this would ensure the accessibility of every part, every corner of the code. So in real life, one of the things that make it difficult to achieve a branch coverage is the thing that there often exist interdependencies among the branching conditions of real life predicates. For example, the conditions like I is equal to j, like even though it looks like a tiny equation expression, but just consider the domain of 32-bit integers where each variable have a probability of more than 5 billion numbers. So it's very difficult for any evolutionary algorithm to evolve these kind of precise values. And it gets even more difficult when we talk about condition decision coverage. Condition decision coverage is a bit more refined form of branch coverage, which in addition also requires that all the individual condition predicates must always evaluate both true and false at least once. So what we propose here, in one of our previous works first, we propose to use the weapon of the enemy against them. And we actually propose to exploit the presence of these very variable interdependencies. So when we exploited the presence of the variable interdependencies in the process of test data generation, we were able to improve the code coverage, and we were also able to do that on a significantly smaller search cost. And we were able to reduce the search cost often between half to 1/3 as compared to other GA-based systems. So how we were able to do that? So the main difference that we brought in the conventional search-based software testing was the use of GE. Grammatical evolution is a grammar-based genetic algorithm which separates the search space from solution space by a grammar-based mapping process. The generic operators of selection, crossover, and mutation are performed on the generic genotype, while as the evaluation is performed on the phenotype. So the conversion between genotype to phenotype is done based on a grammar-based, like grammar is a set of rules. So in our previous work, we designed a simple grammar which was able to generate test data such that it enabled the test data to take interdependent values on each other. And when we were able to generate those interdependent values, we were quickly able to solve those conditions, to satisfy those conditions. Later in the presentation, we would also see one example of that. And more details on grammatical evolution are available in the handbook of GE. So other than the variable interdependencies, there is another thing. There often exist boundary values in the branching conditions or condition predicates of real-life programs. For example, of the form I is equal to 5,000. So again, if we have a 32-bit number, to generate one precise number from a domain of roughly 5 billion numbers, it's really a tough task. And we stick to our philosophy. We again, in this work, propose to use this problematic feature of programs as our strength. So in this work, we propose to seed these constants in the grammar of GE. And in doing so, we not only achieved the success rate of 100%, but we also did that without trading off the efficiency of original GE-based system. In fact, we actually further improved the efficiency by a magnitude of multiple times. So most of the proposed SBST techniques in the literature, they actually target the structural coverage testing. which includes the branch testing or the condition testing. So if we want to achieve the branch coverage, which is the simplest form of coverage for this small program that you can see on this screen, and here's the control graph of the same program. Now, if we want to manually write a test data that can achieve a full coverage for this piece of code, first of all, we need to satisfy the first condition, that is x is equal to 100, to cover the branch 1. So we can write something like that, where the value of x is 100, the value of y and z are not relevant here. So if the condition is satisfied, the branch B1 is covered. Now, if we want to also cover other branches, we need to run our program with a different data. So to cover B2, we need to feed our program with anything where the value of x is not equal to 100. So we can give it something like that, where x is equal to 105. So when we would run this code with this input data, where the values of x, y, and z are 105, 124, and 40 respectively, the branch 2 would be covered. And in addition to B2, the same test data would also cover branch 3, that is B3. And it's very common that whenever a new branch in a code is covered, the subsequent or the following branches, some of them would also be covered because the control would take one over the other paths. Now we are only left with one branch, that is B4. So for that, if we give the program a test data of the form like 105, 124, and 240, now here in this test data, the condition x is greater than z or y is greater than z is dissatisfied. But a very important thing to note here is that the first condition, that is x is equal to 100, should also needs to be dissatisfied. Otherwise, the control would not take the path of B2. So here we can make a conclusion that in case of nested hierarchy of condition predicates, it can become more difficult to achieve a full coverage. So as we can see in our previous example, that to manually generate that kind of test data for bigger programs, that can be a laborious task and that can consume a big chunk of our software development budget. And in the literature, genetic algorithms are the most commonly adopted search technique in SBST. So in SBST in general, any heuristic-based technique is used to find the test data of interest. And the subfield of SBST where we particularly used evolutionary algorithms is called evolutionary testing. So in our previous work, Ariadne have been favorably compared to other well-known GA-based techniques, as it did not only improve the coverage, but also reduce the search cost to somewhere half to 1/10 of the as compared to other GA-based systems. But if we need to create precise constants to satisfy the conditions like I is equal to 5,000, it can be difficult for any GA-based system and also for GE-based test data generated to generate those precise values. So now, as we know that there are often interdependencies among the variables and the variables with the constants in the real life programs. And the same thing is also reported in multiple studies in the literature. For example, in one of the studies of 50 programs, it was reported that 64% of the total predicates were equality predicates. It suggests that there exist interdependencies among the variables. And 77% of them examined only a single variable, which means that in those dependencies, there was only one variable and it included the constant values. Similarly, in another study of 120 programs, it was reported that 98% of the expressions contained fewer than 2 operators, and 62% of them were relational. So it indicates that usually the expressions of the branching conditions are usually smaller and simple in nature. So as we know that there exist interdependencies of both kinds, that is the variables among the dependencies among the variables and the dependencies involving the constant values. So the previous version of Ariadne was able to exploit one kind of interdependencies, that is including only variables. Now, to enable Ariadne to be also able to exploit interdependencies involving constants, we here propose a strategy to seed the grammar. So seeding, is that a new thing in GA-based systems? Of course not. Several studies have shown that seeding strategies can have a very positive impact on the GA-based search process. And in particularly search-based software testing, there are studies which show that direct seeding from the constants from the branching conditions can very significantly improve the structural coverage. So in this situation, we propose a different seeding strategy to inject that knowledge in the grammar, not in the initial population. The reason for the different seeding strategy is that, as we have seen in our previous example, that there can be nested levels of branching conditions. And if we only inject the knowledge in the initial population, those constant values, their value can be changed over time by the operators of mutation and crossover. And it is possible that some of those particular constants are required later in the evolution process to satisfy the conditions in the deeper levels of nesting of a particular program. So this strategy would allow the system to retain those values, and throughout the evolutionary process, those constant values can be used to exploit the dependencies. So this is the overall working of Ariadne. We have a list of objectives, which includes the true and false outcomes of all the branching conditions and condition predicates. The first uncovered objective is selected as a target, and a GE-based engine is used to try to satisfy that target. In case the target is satisfied, the relevant test data is recorded. And it's also seen if there is any accidental coverage, which is very common, that if when we are trying to find a test data for one particular branch, it's very common that some other branches can be covered by accident. So our system also records those accidental coverages. After that, the system checks if there are any further uncovered objectives which have not yet tested. If there are any such objectives, the same mechanism is followed for them. And again, the GE-based search engine is used for them. And we keep on doing that by the time all the test objectives are either satisfied or at least targeted once. The percentage of covered objectives is used one of the fitness measures of any search-based software testing algorithm. So this is the place where the magic happens. This is the design, this is the improved design of our grammar. We have a set of non-terminals. In this set, we have a list of variables. So for this particular program, there are 3 input variables, which is used as an example here. If we want to use this grammar for any different program, the only part we need to modify is the number of variables according to the program and the test. This is the set of terminals that we will discuss shortly. It starts from the start symbol, and the production rules as follows. So the first rule have only one production rule, and it lists all the variables. Now to expand the first variable, we have a few options here. The first option, 0, allows the variable 1 to take the value of 0, which can quickly satisfy 0 value checks. The values of 1 and -1 represent the positive value and negative value domains, which can very quickly satisfy those value checks. Then there is another rule, which is constant. Now, if this rule is selected, it would enable the variable, it would allow it to take the value from one of the constants that are extracted and seeded in the grammar. Then the grammar also allows the generation of random numbers. Now for variable 2, we have the same set of production rules. And in addition, we have one more rule, which is the dependency rule. So this rule would enable the variable 2 to take the value which is dependent on variable 1. So it can be dependent in 3 ways. It can be either the same as that of variable 1, or it can be larger or smaller than variable 1. And we simply make the values larger or smaller by simply adding or subtracting 1 from them. Then for the third variable, there are more dependency rules because now there are previously more variables generated. So using this grammar, let's now go through an example of genotype to phenotype mapping step by step. So we want to expand this start symbol. And for that, we have to make the selections among the production rules. And we would make those selections by consuming the integers in the genotype one by one. So for the first variable, we have first integer in the genotype 73, and total number of production options for variable 1 are 5. So we would use, the GE would use a mode-based function to make the selection. The answer of mode function in this case is 3. On the third index, the option is constant. Now we need to further expand constant. Now, to further expand constant, now we have a list of constants which are actually extracted from the program and seeded here. Now, to make the choice among the constants, we would again consume one more genotype. And we would take a mode with the number of options. Again, 3 is answer in this case, and on index 3, we have constant number 4. So the constant number 4 is stored as the value for first variable. Now we need to generate the variable number 2. Again, we would use a similar mechanism of a mode function by consuming next genotype, and the answer would actually direct us to use the random function in this case. Now to use the random function, we would use the next genotype as seed. Now this thing is very important here again, because the use of a seed from genotype would make sure that every time this genotype is mapped to phenotype, the same phenotype is generated so that the program takes the same flow. Let's assume that the answer is 370. We would store 370 as the value of our second variable in the phenotype. Now similarly for variable 3, we would consume the next genotype and take a mode with the number of options, which is 7 in this case. And the answer dictates us to select the dependency rule. So now the value of variable 3 according to the selected rule should be dependent on variable 1. So to further expand the dependency rule, we would consume one more genotype, and the total number of dependency options are 3. Now the option is selected here is that we have to make this variable larger than the previous variable. So we would simply add 1 in C4, which is the value for first variable, and we would store C4 plus 1 as the third variable in the phenotype. So now to evaluate the performance of this individual, this phenotype is used, and we would run the program with this phenotype, and a fitness value would be allocated according to the fitness behavior of the program. Now to do our experimental setup, we use 2 sets of benchmark functions. Set 1 included 10 numeric benchmark functions, which were heavily reliant on constant values. That is, they involved many boundary values included in them. And then in the set 2, we included some famous benchmark programs, which were also previously adopted by our original Ariadne work. So the triangle classification is one of the most commonly adopted benchmark function. The days function, it is different from the other programs as it accepts 2 dates as input values. And the validity check functions of ISBN and ISSN, they accept an array of 30 characters as input. So for these programs, we used a population size of 50 and 200 generations. But we actually artificially made S1, S2, and S3 as more complex benchmarks, and we made them more difficult testing problems by adding deeper levels of nesting and compound branching conditions. Now, we run 200 independent runs for all the benchmark functions, and here we report their mean performance. When we run the original grammar of Ariadne for these programs, we were only able to hit a maximum coverage between 25% to 75%, and hence we were only able to achieve a 0% success rate. The huge values of average number of evaluations suggest that this algorithm was given a fair chance to evolve the required test data. But when we run the experiments with our improved grammar, we were able to hit 100% coverage for all 200 runs, and hence we achieved a 100% success rate. And the average number of evaluations are also tiny in this case. Now, to see if this improved system also retains the efficiency of the previous system, we also run the same set of experiments on a different benchmarks that were previously. Basically 2 subsets in this set. Triangle, Ray, and QCF were reported in Gadget paper, and they reported the best of their 5 runs. Whereas in Herman and McMinn's paper, the average of their 60 runs were presented. We here present the average of 200 runs of the original system, and we can see that the maximum coverage is always 100%, whereas in the Gadget paper, particularly for the triangle classification program, it was 94%, which is a very difficult testing problem. And we were also able to achieve a 100% success rate always, in contrast to Herman and MC-Min paper. And the average number of executions were also reduced somewhere between half to 1/10 as compared to previous GA-based systems. Now, when we run these programs for our improved system, they retain the same performance in terms of coverage. And in addition, they also further reduce the cost of it, often to 1/3 to 1/10 of the original system. Hence, we can conclude that our seeding strategy not only improved the effectiveness in terms of code coverage, but it also improved the efficiency in terms of average number of valuations. And for the future, like one thing, it can be interesting to see how to see the values examined at runtime, that is dynamic seeding. And we are also actively working on extension of our grammar to accommodate further knowledge, that is the constants and other mathematical operators in that. Your questions and feedback is welcomed. Thank you.
Thank you. So we have now time for some questions. Please write them on the chat or. Oh, okay, so I will start with a quick question. So when you insert, for instance, the constants 0, 1, and -1, it's like you are already inserting knowledge, domain knowledge into your grammar, right?
Yeah.
Right?
Yeah. So this part of domain knowledge, we actually added that in our previous version, so that the zero value checks and positive and negative value checks are quickly satisfied.
Okay.
But yeah, you're true. This is also domain knowledge, but
okay.
we added more domain knowledge in terms of the constant values extracted from the program.
Okay. Okay. So we have a question here from Bill Langdon. The question is, did you compare with EvoSuite?
We did not compare particularly with EvoSuite, but we compared it with other GA-based systems, because with EvoSuite, like in the future, we can also compare with more tools, because some of the tools are using object-oriented programs. And this version of Ariadne is actually dealing with sequential programs. That's a natural extension of this work to also exploit the same strategy in the object-oriented domain. So then we would be able to actually make comparisons with more tools.
Okay. So questions, more questions, please. Okay, I'm going to make another one. So when you are seeding with the constants, so you basically scan the source code for the values that you need to put in the grammar, right?
Yeah. Okay. Like that strategy was also not new, because some of the works in the literature, they were already doing that. But
okay.
The main difference here is that they were using those seeds in their first generation to seed their initial population. But we are using those, we are actually keeping them in our grammar so that they can be exploited throughout the evolutionary process.
Oh, but what you're saying is that they removed after the first, they removed the constants after the first generation.
I get your question. So they don't remove it, but like if we have any seeding in the initial population, those values can be changed over time by the process of mutation and crossover.
Okay,
and
okay.
As we know the nature of software, like branch coverage, there can be deeper levels of nesting. So some particular constants, they may be required on deeper levels of nesting. So they might be required on later stages of evolutionary process. And if we keep them in the grammar, they stay available throughout the search process to be exploited.
Okay, okay, makes sense. Makes a lot of sense. So we have another question by Bill Langdon, and he is asking, can the grammar be generated automatically?
Well, the only difference that you need to make is the number of variables. So it can definitely be automated because it's the same grammar, it's the same design of grammar. So if you just need to write a loop that if there are 10 number of variables, there can be there would be 9 dependency rules and vice versa.
Okay.
The rest of the design, like this is one of the strengths of Ariadne, that it retains the same design of grammar for all the programs to test.
Okay. So any more questions? So we have a question by Douglas Diaz, and the question is, did you test it in C programs?
Yeah.
Okay. Okay. Yeah. So any more questions?
I would just like to add one thing here, like these benchmarks, they are also available, like the link is also available in the paper, and I can also share that here. Like these programs, if somebody wants to further develop on them, because some of the previous papers, they did not make the programs available, that actually kind of restricted the future comparisons. So to facilitate the future comparisons, we have also made the source code available for all the programs used in our previous work and also the ones used in our current work.
Okay, so if you want, I suggest that you can leave the link on the chat after answering the questions.
Sure.
And we have time for one last question by Bill again. So Bill is asking, will it work on other languages?
Well, we have not tested it on any other language other than C, but we believe that there is nothing that stops it from working for other languages, because even the studies that we used to make our point, they were not all on C programs. So in all the languages, there exist interdependencies among the variables in branching conditions. So it to the best of our understanding, it definitely would work for other languages as well.
Okay. Okay, thank you. Thank you all for the questions. And I would like to thank you again for your nice presentation.